Thank you. Let's see what I can do about that. So welcome everybody. I'm here today representing Proxima Fusion. And I know you're all already experts on fusion, thanks to James' excellent talk from this morning on tokamaks. Now we're talking about Stellarators. So from previous episodes, what is a Stellarator? It's this fancy donut-shaped machine which is meant to confine fusing plasma, which is represented here in pink. This that you're looking at is Wettstein 7X. It's to date the most advanced stellarator in the world. It was a research project of the Max Planck Institute of Plasma Physics in Munich. And we as Proxima Fusion want to build onto this experiment, because I have to point out Wettstein 7X does not extract energy from fusing plasma. It simply confines plasma. And what we at Proxima Fusion want to do in the coming years is to take this to the finishing line in mainly two steps. The one that we call Proxima Alpha. Want to be the first stellarator that confines fusing plasma. But once you're not done yet, you want the final step should be to be able to extract energy, because this fusing plasma is releasing a lot of energy, and you want to be able to extract it. Otherwise, you just have a very expensive radiator. The way we intend to do this is with a tool that was very creatively named Starfinder, and that is. So this is a tool, a software framework for fast optimization, because what we need to do basically is to take the thing that I showed you earlier, optimize it, make it into a real power plant. And of this graphic here, there are two main components. One is the plasma simulator that gives us the shape of a plasma and the magnetic field that is necessary to confine that plasma. And through some fancy middleware, we get to the other core of our strategy, which is the parametric CAD. When I say parametric CAD, I mean in particular that we are aiming at having our whole development process as parametric in the sense of automated as possible. And in particular, we don't want to have any old school engineers using their hands with a mouse and clicking for 3 hours every time that we change a parameter somewhere. So this is supposed to be all automated. Right. So now you might be wondering, okay, this is all nice and cool, but where does Phoenix come into here? Okay. Well, thing is when they hire Phoenix comes in here in this bottom right corner where it says first wall. Because when they hired me, they said, okay, you're gonna design the first wall, use whatever software you think is necessary. And I thought, well, Phoenix is absolutely necessary. So now that we are done with these corporate slides, let me take off this funny hat that I'm wearing and put on my usual hat. Now let's talk finite elements. Let's talk modeling and simulation of this specific component, the first wall, which is, as the name suggests, is the first component that is facing the plasma. It's because remember, the plasma is inside and then the whole machine is outside. So this is the first component that the plasma faces, and it has to absorb a lot of radiation and neutron heat that are coming from the plasma, because the plasma chamber is not a friendly environment. Okay, and there's a lot of radiation, a lot of neutrons coming in, and some of the energy from the neutrons we want to extract, but the energy from the radiation in particular we want to stop, because otherwise the machine melts, the magnets melt, the wall melts, everything melts, and no power for anyone. Okay, so very important. We need to cool this thing down to avoid it melting. Now, what does the first wall look like? It looks like this. It's similar to the pink plasma thing that you saw earlier, just around it. Okay. And now, as I said, there are two. So we're doing thermal modeling of this thing, and there are two main sources of thermal energy, sources of heat. One is the radiation. This is just electromagnetic radiation coming straight from the plasma. I don't need to go into the details of how this was computed, because this was just some easy pre-processing computation. The interesting part is that this thing that you see now can now be loaded into Phoenix X thanks to some recent functionalities implemented by me with the invaluable help of Jorgen, developer extraordinaire. and can be then interpolated into our actual computational mesh as an initial boundary, as a boundary condition. And so I don't know if you can see the scale, because the picture was a bit resized, but here it says 0.35 megawatts per square meter, and here it says 0.75 megawatts per square meter, just to give you an order of an idea of the order of magnitude. So this is the first source of energy. The other source of energy comes from the neutronics, and this that you're looking at is the neutron load. This is computed through OpenMC, through a Monte Carlo method, and here we're talking about 40 megawatts per cubic meter. This is a volume source. And just like before, this can be now loaded into Phoenix as a function used as a source term, interpolated into our actual computational mesh, etc. So we're back to the wall. We need to cool it down. How do you cool down a thing? Well, the easiest way is you carve a pipe into it, and you run some coolant in it. Right? Coolant comes in cold, extracts the heat, goes out. New coolant comes in, extracts more heat. Okay? And as I said earlier, I mentioned parametric CAD. You will hear me repeating this mantra a couple more times, and not just because I'm contractually obligated to do so, but when we fully exploit the power of parametric CAD, we are free to change the design of these walls, of the pipes. So for example, here you see for different hydraulic diameters. Now, the hydraulic diameter is a fancy engineering term for the side of the pipe. And for the simulations I'm going to show today, we're going to use the 12 millimeter hydraulic diameters because it has good properties for what we're going to do. And yeah, so as I was saying, we can vary the side, the pitch, which is the distance between, basically the distance between two lines. We can tune everything that we want, the distance between the plasma, which is here, and the pipes. Yeah, we have full control, no clicking of any sort. And we can even add layers. For example, here you see that I added a layer. The blue is Eurofer, which is a futuristic metal alloy developed by ITER, I believe. No, developed by the fusion community, and it is very suitable for this kind of applications. And the red small layer is 2 millimeters in this picture. It's tungsten, which is very, very good for, again, it has other interesting properties that make it suitable for being the first. It's called the armor. So it's for being the first layer between the plasma and the rest of the machine. Now, again, parametric modeling, because in our simulations, we don't have 2 pipes, as I showed earlier. We don't have 10 pipes, as I'm showing in this picture. We have many pipes. We can have very many pipes. Like here, you're looking at a half module, which is the unit of symmetry in a Stellarator, which is a partially symmetric machine. And this is like 15,000 pipes, order magnitude, something like that. And these pipes can be quite tricky to design, can be quite complex. You see, for example, in this screenshot, this pipe comes in straight and then has to do some twisting because you want the lower side of the pipe to be as parallel as possible to the surface, because otherwise you lose a couple of millimeters there. And in this kind of applications, even a couple of millimeters can make the difference between a solid and a fluid wall. And if you're asking yourself, wow, what kind of code does parametric CAD modeling? Well, sometimes it's this kind of code that you need to write to do parametric CAD modeling. And this gigantic thing is just to compute maybe the angle at which a certain line comes in or not. And I don't envy the guy who's getting to review this. Anyway, now that we get all the preliminaries out of the way, show you some equations. Yeah, so we're solving a steady state heat equation where we have as a source term the neutron load that I showed you earlier. And on the plasma facing surface part of the boundary, we have the radiation load. Well, then the backside is insulated. And on the pipes, which is the interesting part, we have a Robin boundary condition to model heat extraction, which is proportional to the temperature difference between the actual unknown temperature and the temperature of the coolant. Now, interesting twist, the temperature of the coolant is not constant. It depends on the position because you decide the input temperature, the inlet temperature to the coolant, but then as it flows through the pipe, it absorbs heat, so it gains in temperature. And so what this means is that you have a constraint for each pipe, for each of your hundreds or maybe thousands of pipes, you have a constraint to satisfy that tells you that the total heat that flows into the pipe has to be reflected in the change of energy, which is reflected into the temperature difference. So basically the outlet temperature of the pipe. And this means that we cannot solve this equation in one go. We have to do one of my favorite things, which is a fixed point iteration. So we solve for the temperature. This now is a fixed iteration on the index J, you see here in this equation. So we solve for the temperature for an initial guess, and then we compute the heat fluxes on each of the pipes individually. And then we update the temperature of each of the pipes individually, and then we solve again. So until convergence, till the difference between two successive solutions is smaller than a tolerance. And there's another twist. If you have two parallel pipes, you don't want the coolant to flow parallel. You want it to flow counter-parallel so that the cooler end of one pipe is right next to the hotter end of the other pipe and vice versa. So this helps even out the heat a little bit more, which means that in pre-processing, we have to tag the pipes. And for example, here I tag with a fictitious position going from 0 to 1. And this was another interesting pre-processing step. And so using then this, we can say, okay, the temperature will vary linearly from 0 to 1 or from T inlet to T outlet. Okay, so time to wrap up. I'll show you some simulation results, ignoring the artifacts due to the geometry constraints. But then you can see this is just one column of pipes. And the most important feature that we can get from this picture is the temperature. The maximum temperature is 520, which is, very importantly, less than 550, which is the melting temperature of the Eurofer. So that mission accomplished for that. If we slice it, we can see very nicely the distinction here, with the boundary here between the tungsten and the Eurofer, which have two different thermal conductivities. You can see that this section here is close to an inlet of a pipe. This one is close to an outlet because temperature is lower here, higher here. And if you look now at the outlet temperature of the pipes, which is very important because it's what lets you extract energy from the machine in part, then we see that we have an increase in the temperature of the pipes that goes up to about 70 degrees. And this is very important because this is consistent with what we see in the literature for tokamaks or other similar machines. So now, concluding, let's say microscopic and macroscopic conclusions of the first kind. What you saw is parametric CAD design of the first wall. Thank you, Open Cascade. Input gathered from other sources, while integrating Phoenix to the bigger ecosystem, thanks also to the most recent functionalities. And the juicy part, the thermal simulation of the cooling in the first wall. I was very happy with that. And in a macroscopic scenario instead, what this work means is that we can give green light to the rest of the team, the other components, to design their parts, knowing that they would not melt, hopefully. And if at any point of the presentation did you think, oh, this is so cool, but keep in mind that we are growing, we are hiring. We're not a university, so we're not afraid of paying good money for good talent. So thank you very much for your attention.